All right, so a lot of what we're going to talk about today is going to be similar to what we went over yesterday when we did that Desmos activity, where we were talking about dilations and just kind of the basics. We kind of went over what is the scale factor, what does it mean for it to be getting bigger versus smaller, and you did do a little bit with the numbers or like distances between points on shapes and like figuring out how maybe do you use the scale factor to actually perform the dilation. So today we're going to just continue to maybe recap some of what you guys figured out yesterday and we also talked about yesterday at the end of class, but also then start implementing practice on how do we actually do these dilations. Okay, so if you guys had to tell someone in your own words what it means to dilate, what would you guys say? What does dilate mean to you in like non-teacher terms? How would you explain to someone in class if they were gone yesterday and they didn't know what we talked about? How would you explain to them what a dilation is? Quentin? An object getting bigger or smaller. That's perfect. Okay. Now, the only thing I might add is we also talked about yesterday that it would be getting bigger or smaller in all directions, right? Not just in one direction, because that would be maybe considered a stretch then. But I like what he said there. So I'm going to go ahead and write down his thoughts, which was an object. So I'm going to say objects getting bigger or smaller. And I'm going to say in all directions. Yesterday we used that word proportionally to describe that. Proportionally just means everything is going to be affected by the scale factor, not just half of the shape, or it's not like we're going to double this side and we're going to triple this side, because then it would actually start to make that shape look a little weird. And it could even start to change the shape. But when we do a dilation, I'm going to add this on here too, put a little star here next to it, the shape will not change. The shape is going to stay whatever it was. So if it was a square to begin with, it's going to end as a square. If it was a triangle, it's going to end as a triangle. We may not see shapes though. So I'm kind of glad that Quentin said objects, because it doesn't have to be a triangle. It doesn't have to be a shape. It could be a line segment. It could be a distance that we're talking about from like this town to this town, and maybe we're trying to double our trip or double the mileage that we traveled or something like that. So it doesn't have to be strictly shapes. It doesn't have to just be triangles, quadrilaterals, those kind of things. And we'll see a little bit of that today as well as we get going. Okay, what letter did they use when they were talking about the scale factor? K. So I'm going to go ahead and write up here at the top, K, anytime we see that, means scale factor. I don't know why they use K. Okay, I don't get to make those decisions in math. I'm not the one who was like deciding we're going to name this, this, and this. Like that was done thousands of years ago. So K is just what is they like as a collective in the math world we use to represent scale factor. Again, I don't know why. I don't know what their reasoning was for that. But anytime you see K in a problem, they're talking about the scale factor, or they're talking about some kind of constant that is going to impact everything in the problem. So even in other senses of math, you might talk about like proportional problems, or like talking about like inverse relationships or direct relationships. There's going to be a scale factor of K in those to kind of talk about how are these two things related to each other. So it's kind of like the same idea as that scale factor. It's going to be the same for everything in the problem. Now, when we had scale factors yesterday, we worked with like the slider on that activity to kind of decide when do the scale factors start to make shapes bigger? When do they start to make them smaller? Do you guys remember what did the number have to be in order for it to get bigger? More than one. So I'm going to write down here when it says, the enlargement word is here. This means that a shape's going to get bigger, or an object. You could keep using the word object if you wanted to. And I'm going to write K is greater than 1. And what did it have to be if it was a reduction? Under 1. And that also means that the shape gets smaller. So K is less than 1. I'm also going to add on here, though. We didn't talk about this yesterday, but I'm going to add it on because you'll probably see this somewhere else eventually, is that it would also have to be bigger than 0. Okay? Because I want you to just think about that for a second. If I had a scale factor of 0, what would happen to my shape? If it was 0? It'd be nothing, right? Because anything times 0 is 0. So if my scale factor is 0, it doesn't really make a lot of sense to do that because it's going to completely eliminate the shape. So when I think about a reduction, I don't want it to equal 0, but it could be as close to 0 as possible. It could be 0.000000001 or even more zeros in front of that 1, but it doesn't want to be 0 because then the shape just is going to go away. Now this would be that case of sometimes you'll see this written as a decimal like 0.25, 0.75 or something like that, or you might see fractions, a half, 3/4, maybe you'll see something like 2/3, 1/3, 1/5. But be careful that you don't make that assumption that just because you see a decimal or just because you see a fraction, that does not always guarantee that it's going to be a reduction. If it's 2.5, that's an enlargement. If it's 1.5, that would also be an enlargement. So you just have to watch how they're writing those things. All right, now let's talk about the notation. Down below, they have our notation for a dilation here. And last semester when we talked about reflections, rotations, translations, we had notation for those as well. Do you guys remember when we had reflections, what letter did we use for that? Was it a big R or a little r for reflection? You remember? It was little. If we were doing reflections, it was a little r, and then it would say like x-axis or y equals x or something like that. What was it when we did a translation? Big T. And then you had maybe like a vector, or it would actually have like the rule. It had like an arrow, and it would say like x, you're adding or subtracting this number, y, you're adding or subtracting this number. And what did we use for a rotation? Big R. And I actually think this notation looks kind of like our rotation one because it has some of the same pieces. Like if this was a capital R up here instead of a D, and like we had this letter was always there as well on rotations, and then instead of like K, it would say like 90 degrees, 270 degrees, something like that. And then this would also look the same, like whatever you're rotating would come after that in parentheses. So let's kind of think about that when we look now at this dilation notation. We're using a capital D for dilation, which makes sense. Okay, so I'm going to go ahead and just underneath this, I'm going to write out what these pieces mean. So capital D means dilation. Now think about when we did rotations, that letter that followed it, that was the center of rotation. That was where we like put our pencil before we actually turned the shape, if we had it like on patty paper or something. What is that O representing today though now? It is the origin, but it's also representing the center of what? Dilation. Because it could be any letter. It doesn't have to be the origin. It could be an A, a B. It could be any point on the coordinate plane. It could be on the shape. It could be off the shape, in the shape. It doesn't matter where it is. But yes, this letter here is going to represent center of dilation. What does the K represent? Good. So I'm just going to put scale factor there. And then in parentheses after that, that x, y, that's just talking about what would be dilated. So maybe a coordinate for this one, but it could be triangle ABC, quad QRST. Could be something like that instead. And then you're talking about this is the thing that I'm doing all the dilation stuff to. So when you're looking at notation, you want to be able to pull out where's the center, especially when we're performing dilations. Where's the center of dilation at? Is it the origin or is it another letter? And then what's your scale factor? And just take a quick look at that scale factor. Is it going to get bigger? Is it going to get smaller? We should be able to figure out all of that by just looking at our notation. The first set of examples I have here are going to just be deciding if the situation would have been an enlargement or a reduction. We're not performing them yet. We're just looking at these cases and figuring out what do we think happened here. So if you guys look at A, they write this one that says scale factor of 5 to 2. This, how they're writing this, is called a ratio because of the numbers and like the dots in the middle. That's how we write ratios in math. It also could be represented like 5 over 2 as a fraction. And then underneath it, it says image to pre-image. They're trying to tell you something with those words about what came first, what came last, or like what was the original, what was the new shape. Does anyone have an idea or a guess on if they think this would be a reduction or an enlargement?
Reduction.
A reduction? Do you know why?
The second, the purple shape has like the marks on it.
Oh, you're looking at B?
Oh, my bad.
That's okay. No, let's do B. So what, continue what you were saying.
The purple shape has the marks on the letters.
Yeah, the primes, right?
Yeah.
Mm-hmm. So this was the original shape, and this got obviously smaller.
Yeah.
And we also see these markings. That's perfect. So yes, this one is a reduction. Okay, let's come back here to letter A. I'm just going to zoom in on it. What do we think about this one? A reduction? How come, Brady?
There's a ratio in the image and pre-image too. Like the 5 is the image and 2 is the pre-image.
Okay, so when we...
know it would be an enlargement.
Oh, why are you switching your mind?
Never mind. I don't know.
No, I want you to keep going because I think you're almost there. What made you all of a sudden say...
2 is the pre-image.
And what does this mean? What's pre-image mean?
It's the first one.
The first one, the original. And this means new, like what we did to it, okay? Someone first period did the exact same thing you just did. They said reduction first, and then they started talking through it, and they're like, oh, wait, no, I said that wrong. That's fine, okay? This means old. This means new, or original, new, however you want to think about that. So we started at 2. We went to 5. It got bigger. So it's an enlargement. Another thing you could do is you could look at this as a fraction. When you set up like the scale factor, you're always putting the new dimensions over the old dimensions. So we would put 5 over 2. Now, I know it's a fraction, but that does not mean that it's guaranteed to be a reduction. Because if I really think about this, this is 2.5. That is bigger than 1. So it's still an enlargement. Either way you think about it works. Some students will even do this. They'll put an N on top of the 5 for the new shape, and they'll put an O on top of the 2 for the original shape. Whatever helps you distinguish, this is where I started, this is where I ended, so that you can see, did it get bigger or smaller? Any of those things is going to work for you. All right, we got one more in this section, C. What do you guys think about this one? Did it get bigger or smaller? How do you know, Aaliyah? The scale factor is 5. This number right here tells us what's going on. That's greater than 1. So yes, it would be an enlargement. Very good. All right, do we have any questions on those first 3? Okay, now we're actually getting into performing some of these dilations. So if you kind of look down here at number 5, it says below is the dilation of segment AB centered at O with a scale factor of 0.5. And then they go on to say OA is 6 centimeters, OB is 8 centimeters, and AB is 4 centimeters. All of that is labeled for me on my picture already. But the problem is wanting me to do is figure out how much all these measurements are of all these other pieces. Now, I could go one at a time and go through them. You can do that yourself if you'd like to. What I like to kind of do actually is just zoom in on the picture, and I like to fill in anything that's not marked by just using my scale factor. Because then when I go to fill in all those blanks, all I have to do is just go over to my picture and grab my numbers and drop them in for my answers. So my scale factor is a half. This is the original shape. If my scale factor is a half, should it get bigger or smaller? And it does, right? So that makes sense. Now, if I started with 4, how would you figure out how much this is?
Divided by 2.
Why do you say divide by 2 when the scale factor is a half?
Because, so if you put 4 times it by a half, you'll get 4 over 2, and then if you divide that, you get 2.
You're thinking like this in your head, right? That's perfect. This becomes 2. Okay, I'm really glad though that you said times a half, because last period somebody said they took 4 divided by a half. And I kind of went over with them though, if you think about that, I'll just write it out over here. You don't have to write this down. But if I were to divide by a half, the rules in math say when you divide by a fraction, you have to multiply by its reciprocal. So really what happens here is you're taking 4 times 2. And actually you get up to 8. So that's incorrect to think I want to divide by a half. We always want to think we multiply by our scale factor, even if it's a fraction. Now, in this case, because our fraction is a half, we can just think divide by 2, because that's really what's going on. Just like if my fraction was a third, I could think I'm dividing by 3. But sometimes you might get thrown like a really complicated fraction, like 7/5, and maybe then it would be wise to just multiply. And if you need to, you can always use a calculator to help you multiply if you're dealing with like a real crazy scale factor. Okay, but I'm glad you said that. So 4 is where we started with. If you divide 4 by 2, you get 2. So this segment here, A prime to B prime, should be 2. What else could we figure out? O to A is 6. So what could we use the scale factor for to help us find?
Half of 6 is 3.
Half of 6 is 3. Where would that go?
O, A prime, A prime, A.
So in this case, it would go here and here, right? So this would be 3 and 3. Okay, just follow along with me for a second. What if the scale factor was 1/3 instead? What would be 6 times a third? 2. So this would have been 2, and this would have been, careful, 4. Because 2 and 4 gets you up to 6. So you're not always guaranteed to cut them in half. It happens on this one because of the scale factor we're working with. But if we had a different scale factor, it might change those numbers a little bit. Okay, so then how about up on the top there? That whole thing is 8. Your scale factor is a half. 4. And again, 4. But again, if my scale factor was different, it's not going to cut that in half. It's going to kind of skew it a little bit. So just don't make that assumption that everything just gets split evenly here. Okay, now that we have everything, I think, labeled, we should be able to come over here and just fill in our answers. So what would we write down for letter A? 2. And let's go ahead and put a label. What are they saying how much everything is? In centimeters. So 2 centimeters. How about for B? 4 centimeters. C?
3.
D?
3.
E?
4.
Okay, now F is talking about a ratio. I kind of brought that up earlier today with that first example on number 4. The ratio of OA prime to AA prime. So how much are those measurements? 3. So I would write it like this, 3 to 3. That's my ratio. Can you reduce that though? Yeah, what would it actually reduce to? 1 to 1. So if we can reduce ratios, make sure you take that extra step to do that. Even if it was like 3 to 6, what would 3 to 6 reduce to? 1 to 2. So just make sure when you're setting up ratios that you check, are they reduced? All right, any questions on this one? Okay, let's come down here to the last one. It kind of resembles like a number line a little bit. We just don't have numbers on there. We have letters. But up in the directions, it says that each unit is 1 centimeter. So that means like between any 2 spaces on this number line is 1 centimeter. So in this case, like any 2 dots, or you can think about any 2 of those slash marks, that's 1 centimeter here. Now, if we look down below, we've got a lot of that notation. that we kind of talked about earlier with like the capital D, and they're giving you your center and your scale factor. We want to take all of that into consideration because that's going to help us know how we perform these. Now, if you just take a peek before we even begin these, A and B look pretty similar. C is different. What's different about C? What's different here compared to there?
You have to find the pre-image.
You have to find the pre-image, okay? Because I gave you the answer. So that's a little different. What's different about this one?
It's a negative.
There's a negative scale factor. We haven't talked about negative scale factors yet. Okay, so we'll get into that in just a second. But let's start with A and B because those are, I would say, like your normal cases because they're the ones that you're going to see the most. So if we look at A, I'm doing a dilation. What's my center of dilation for A? R. And what's my scale factor? 3. Okay, those are both important things. So 3 means it's going to get bigger. R means that's the letter that we're kind of starting our dilation at, and it's not going to move at all. So anytime that you have your center, that's going to be the letter that your answer is going to start with. Okay, so that's just something that you can use as you're filling these out. Now I'm starting with segment RT. How long is RT? 1, because they told me that each unit is 1. So this is 1 here. I would take this segment 1 times my scale factor of 3. So I'm just going to write that underneath it. What is 3 times 1? 3. So my new segment should be 3. 3. But you start at R and you go over same direction, like you still go towards T, but instead of going over 1, you go over 3 now. So where would you end? W, because if you start here, you go 1, 2, 3. R, W, and go ahead and put your segment notation bar on top because we know how to notate line segments. We learned that last semester. If you need to mark up your line segment like I did there with like kind of doing the hops, do that. You can do that and then erase and start over. You don't have to just do this all mentally if it's too much. Okay, B. What's my center? W. That means we're going to start at W's. I'm just going to put a little dash through that letter so I kind of know this is where I'm starting. What's my scale factor? 1/2. So is it going to get bigger or smaller? Smaller. Now, what did I start with? W to what letter? M. Now that's going the opposite direction. Like we're going to the left, but that's okay. So I'm just going to count 1, 2, 3, 4. So what's 4 times 1/2? 2. We kind of talked about that earlier today. So you still start at W, but this time you only go over 2. And where would you be? T. And I like to sometimes do it on the bottom, like 1, 2. Especially if I'm using my number line to like help me out here, kind of going one set on top, one set on bottom helps you keep them separate. So W, T would be my answer there. All right, does anyone have questions on those first 2 before I start to switch it up? And I just want to reiterate, it doesn't matter if it goes left or right. You just follow that direction when you're dealing with that positive scale factor. You just keep going in the same direction that it was going originally. All right, now we said on C, this one's a little different because it's backwards. Like you said that they're giving you the image instead of giving you the pre-image. So we need to figure out what they took that scale factor times to get to our answer. Now our scale factor for this one is a 4. So I took 4 times whatever this segment is, I'll call that a question mark, to get my segment PR. Well, how long is PR? 4. So you're really asking yourself 4 times what is 4? 1. So I need a segment that's 1 centimeter long, and it starts at what letter? P, and it goes towards R. So it'd be P to W. Same kind of thought process. It's just you have to think a little bit about, okay, I'm going backwards here. So what did I take my scale factor times to get to my last segment? Okay, let's talk about D. We have not seen a negative scale factor yet. And we didn't even talk about negative scale factors yesterday. Anyone have an idea what might happen here? So let's just look at what we know we can pull. Do you have something, Brady?
It goes so it's going left to TM.
Okay.
It'll go right since it's negative.
Since it's negative. If I flip directions, kind of like a reflection, right? Yeah. So what he said, if you didn't hear him, was since TM is going to the left, when you do your new one, you're going to have to flip directions and go to the right. He's correct when he says that. When we have a negative scale factor, that doesn't mean your dimensions are going to become negative. It wouldn't make sense to have negative centimeters. Okay? If you tried to go to the store and like tell someone you needed negative square feet of flooring, the person working is going to look at you like you got two heads, because that doesn't make any sense to get negative flooring or to get negative length of fabric or whatever it is that maybe you need to go. Everything when we talk about distance is positive. So I know there's a negative scale factor. And if I look at TM, how much is TM? 2. So I know some of you are thinking, well, -3 times 2 is -6, and you're not wrong. Okay, but we're not dealing with normal numbers here. We're working with distances. So I'm not even going to mess with the negative. I'm just going to think about the 6 for right now. But like what Brady was saying, if I start at T and I try to go 6 this way, do I have room? No. So that should also maybe be a clue of like, that's the wrong way to go. So we do need to flip it backwards to reflect the negative scale factor. So instead, if I start at T and I go 6 to the right, where do I end? H. Does that make sense, guys, with the negative scale factor? You're basically doing a reflection. Even if we were on the coordinate plane, if we had a negative scale factor happening, it's going to take that original shape and it's going to reflect it the opposite direction using those projection lines. Those projection lines can go in both directions through the center and through the shape that you're dilating. All right, do we have any questions on that last one with those number line, kind of the number line problem? Okay. Let me get this stopped.